We're on page 20 of the notes, and in this mini lecture we're going to do an example of Euler's method. So use Euler's method to numerically approximate the solution of this differential equation. Now you might note, just by looking at it, that there is an exact solution to this. You could antidifferentiate both sides. You'd have a constant of integration, but this initial condition would allow you to find that constant. Okay. But the reason that we do Euler's method on this is just to kind of illustrate the error. Okay, so recall what Euler's method says. Essentially, we're going to have a meshing of 0 to 4. So we've got our x-axis here. And we're going to mesh it up into step sizes of 0.5. So that'll be 2, 1, 3, 1, 2, 3. No, I think this is actually the right one, sorry. So we're going to approximate it at each of them. So this is 0.5, which we'll call x1, x2, x3, x4 is 2, x5, x6, x7, and then x8 is 4. So obviously x3, for example, is at 1.5. So Euler's method says if you've got a function that's defined on this thing, we can approximate the value at each point, which I'll call y of xi. It's approximately equal to what I'm calling yi. And I'm going to put in a plus 1. Now all this plus 1 really means is that it's the next point. And the y value at the next point is equal to the previous y value plus the step size. And what I'm going to use now is, instead of using the big F of x, xy, which I'm going to use y dashed of I, because the way the formula is set up is it's dy dx is equal to f of xy, and sure, dy dx is nothing but y dashed. It's just it's a more kind of compact thing. So the next y value is the previous y value plus the step size times the previous slope. So the plus 1 means next, in the sense of this is the next one, this is the previous one. The step size remains the same throughout the question. Step size is the distance between these, and they're all 0.5. Okay, so yeah, that's what I said there. So we calculate as follows. So the starting value is 1, okay? And then what have we got? So at 0.5, that's at x1, that's what we're calling y1. It's the previous value, which is 1, plus the step size. Now I have the step size over here, but of course multiplication, the order doesn't matter. So here's the step size, and times the previous slope. So I'm going to probably have a little table down here in a minute, just to show you. Okay, so we'll do our little table here. So we have the x values and the y values. So we started at x equals 0, y is equal to 1. Now we're looking at x equals 0.5. What is the y value? Okay, so we have previous plus step size times the previous slope. So when we're at this point, the previous slope is determined by what's going on here. Now here the slope just depends on x, so I need to put in the previous value of x. So I put in x equals 0, x equals 0, x equals 0, and I bang that all into the calculator and I get 5.25. Now I go again to the next point, which is 1.0. So I do y of 1 is approximately what we call y2, is 5.25, the previous y value, plus the step size, which doesn't change, times the derivative at the previous point. Now, when we're at this point, this is the previous point. So I need to evaluate the slope, the dy dx, at the previous point, which is this 0.5. So I substitute in x equal to 0.5 in there, and I get out the number 5.875, which I'll just record here as 5.88 for space. And then I keep on going. You can continue to work by hand, but of course we're going to look at this in Excel, and then later we're going to look at this in VBA in your first lab. Okay, so you just keep on going. We'll do one more by hand. So, well, we won't use a calculator. We do y of 1.5, approximately the third y value, which is equal to the previous y value, which at this point is 5.875, plus the step size, which is 0.5 times the previous slope. And the slope is this dy dx, and we evaluate that at the previous point, and the previous point to 1.5 is 1. So we're going to have minus 2 times 1 cubed, plus 12 times 0.5 squared, 1 squared, minus 20 times 0.5, plus 8.5. Jeez, I've done it again. My bad. Sorry. Sleep. Oh, it's a bit of sleep at the start of the year. And then you bang that into the calculator. If you can, you'll do equals at full precision. But if there's loads of decimal places, you might do an approximation. And then those rounding errors. So you got the errors from the method not being very good. And if you do rounding, you'll get more and more errors. Errors on top of errors. Okay. And you keep on going like that. So let's see what we get. So if we keep on going, now these numbers look very different. Oh no, they don't, sorry. So we can go back here and put in the 5.125. That's what it says. Yeah, 5.125. So cheat. Okay, so if we keep on going, you can plot your solution. So essentially this is what we've done. We keep on going. Yeah, this is what we get. So here we see the yi values that approximate y of xi. So for example, here at 2.5, so this is the coordinate 2.5, 4.75, and that 4.75 is supposed to approximate the true solution at 2.5. And it's the 1, 2, 3, 4, the fifth point. So we call this thing y5. So y5 approximates there. As it happens, solving this differential equation by hand was unnecessary. Sorry, this is quite bad. That should say approximating. Approximating solutions to this differential equation was unnecessary, as we could solve it exactly just by anti-differentiating. So this is the exact solution. So I can plot the exact solution along with the approximation. So here we have nice colors, happy days. So here we have the exact solution going along. Now, as it happens, we've plotted the exact solutions, but really I don't think I can, no, I can't. Let's add a white here, which would be cool. Do I have a white? No, but if I did have a kind of a, yeah, I don't, yeah, I shouldn't be able to do it. Anyway, see all these points here? Now Excel has just kind of made them up. We don't really know what's going on there. So the only real points of reference are these. They were calculated by Excel. Now you can see we've got a fair bit of error, so be it. So for example, if we talk about y5, that's here. So this is, I'll just write down the y value here, 4.75. Not a very good approximation to the true solution at this point, which is 2.719. Okay, so they're just the y coordinates at those points. So it approximates it. You actually get some kind of, there's some similarities there, but it's not great. As you see from previous graphs, if we move too far away from a point, the tangent line typically moves away from the curve and is no longer a good approximation. So what I'm talking about there is, if you look at the very first approximation, so this is the tangent, and it's actually one of the things about this. So Excel hasn't actually drawn it very well. If the true curve, see the way the slopes, if we zoom in, see the way these slopes here are different. The true solution would have done would have started off at the same slope. So it probably looks more like that. So the point is anyway that if you're very, very close to zero, the tangent, which is the blue line, and the orange, which is the curve, they will be close together. But as you move away from the point, the approximation is not guaranteed to be good forever. And so you're getting these big errors here, this big difference between these. And to be honest, that's where most of the error comes in. And we'll come back to that point a little bit later, and we'll start to understand where the errors actually come from. Okay, so if you want to stop this big error, we need to decrease the step size. So if we didn't go as far as 0.5, suppose we only went as far as, say, 0.1, then like if this orange curve that I drew is the correct one, there's very little error there. We'd have a much better chance of staying close to the true solution. Okay, so this is the exact problem. Here's the step size, and here you see just what I was saying. If I pick that small step size, the error here is small. Now, as it happens, the error builds up over here, and by the time you get to here, you have an issue. Now, we're going to, as I said, talk about that later. If you want to reduce the errors further, so basically, suppose we're interested maybe the error at the end. I might call this the global error. Epsilon g, that's the global error, the error at the very end of the approximation. If you want to make that smaller, like here it's pretty much undiscernible, use a smaller step size again. Now the problem is, like here, if we look at the number of calculations minimum, now this is only, okay, number of calculations. So there's 100 calculations to here, so there's 400 calculations. And what if I was interested in this, not from 0 to 4, but 0 to 4,000? You're getting into serious problems here, okay? So that's the first of our little mini lectures.